Design equations of flow reactors. For a batch reactor, we saw that conversion increases with time spent in the reactor. For continuous flow systems, the conversion x is a function of reactor volume V. So, if Fa0 is the molar flow rate of species A fed to a system operated at steady state, then Fa0 times x, it will be equal to the moles of A fed by unit time times the mole of A reacted divided by the moles of A fed, which is the conversion x. So Fa0 times x is equal of the moles reacted by unit of time. So we will have that the molar flow rate at which A is fed to the system, which is Fa0, minus the molar flow rate at which A is consumed within the system, which is Fa0 times x, is equal to the molar flow rate at which A leaves the system, which is Fa. Rearranging terms, we will have that Fa is equal to Fa0 times 1 minus x. The entering molar flow rate of species A, Fa0 moles per second, is just the product of the entering concentration Ca0, which is mole per cubic decimeters or mole per liter, and the entering volumetric flow rate, V0, which is liters per second. In the liquid phase, Fa0 is equal to Ca0 times V0, so Fa0 is equal to the concentration A0 times the volumetric flow rate at the entrance. For liquid system, the concentration at the entrance, Ca0, is commonly given in terms of molarity. For example, Ca0 equal to 2 moles per liter. For gas system, Ca0 can be calculated from the entering temperature and pressure using the ideal gas law or some other gas law. For an ideal gas in the gas phase, Ca0 will be Pa0, which is the partial pressure of A, divided by the constants of the gases R times the temperature T0. And this is equal to Ya0, which is the mole fraction of A, times P0, which is the initial pressure, the total initial pressure, divided by the constants of the gases R times T0, the initial temperature. And the intermolar flow rate is equal to Fa0 equal V0 times Ca0, but Ca0 is the expression that we just saw. So this will, Fa0 will be Va0, the volumetric flow rate, times Ya0, P0 divided by R, T0. Here, Ca0 is equal to the entering concentrations in moles per liter. Ya0 is equal to the entering mole fraction of A. P0 is equal to the entering total pressure in kilopascals. Pa0 is equal to Ya0 times P0 is equal to the entering partial pressure of A in kilopascals. T0 is equal to the entered temperature in kelvins, and R, the ideal gas constant, is equal to 8.314 kilopascals liters divided by mole Kelvin. We need to take care that according to the different units of pressure, concentration, and temperature, we need to choose the adequate R, because R is in very different, it has different values for different units. So the size of the reactor will depend on the flow rate, on the reaction kinetics, on the reaction conditions, and the site conversion. Let's first calculate the entering molar rate. CSTR, also known as back-mix reactor or BAT. The CSTR mole balance equation is that the volume is equal to Fj0 minus Fj divided by the rate Rj. So when applied to species A in the reaction A plus the coefficient, stoichiometric coefficient B divided by stoichiometric coefficient of A times B, the reactant B, will give us C divided by A times C plus D divided by A times D. This can be rearranged and the volume will be equal to Fa0 minus Fa divided by Ra when we are talking about the reactant A. We now substitute Fa in terms of Fa0 and x, and we remember that Fa is equal to Fa0 minus Fa0 times x. Then the volume will be Fa0 minus Fa0 minus Fa0 times x, all that divided by minus Ra. Simplifying, we see that the CSTR volume necessary to achieve a specified conversion X is when there is perfect mixing, the volume is equal to Fa0 times X divided by minus Ra, where this rate, as we are talking of CSTRs and is perfectly mixed, then the rate is evaluated at the exit because the rate is the same in all points of the reactor. That's something that we must to remember. Now, the tubular flow reactor, the PFR. We model the tubular flow reactor as having the fluid flowing in fluid flow. And we remember that in fluid flow, there are no radial gradients in concentration, temperature, or reaction rate. We remember that all the variations in these variables, concentration, temperature, or reaction rate, are only in the axial direction. As the reactants enter and flow axially down the reactor, they are consumed and the conversion increases along the length of the reactor. To develop the PFR design equation, we express the mole balance equation for species A in the reaction as minus dFA divided by dB is equal to minus Ra. And for a flow system, Fa have previously been given as Fa equal to Fa0 minus Fa0 times x. So if we differentiate this expression, we will have that dFA is equal to minus Fa0 times dx, because remember that Fa0 is a constant and the derivative of a constant is 0. Then we will have that Fa0 times dx divided by dB is equal to minus Ra. We now separate the variables and integrate with the limit that at b equals 0 is when the conversion is equal 0. And we obtain the flow reactant volume necessary to achieve a specified conversion x, and we will have that the volume will be Fa0, the integral from 0 to x, dx divided by minus Ra. To carry out the integration, we need to know how the reaction rate minus Ra varies with the concentration or conversion of the reacting species. And that's something that we will see later on. Packed bed reactor. Packed bed reactors are tubular reactors filled with catalyst particles. The derivation of the differential and integral forms of the design equations for packed bed reactors are analogous to those for PFR. So here we have the expression for packed bed reactors. We will have that Fa0 times dx divided by dw is equal to minus Ra prime. And we must remember that for PFR, instead of dw, we had dv. This differential form of the design equation must be used when analyzing reactors that have a pressure drop along the length of the reactor. In the absence of pressure drop, that means delta P equals 0, we can integrate the above equation with the limit x equals 0 at w equals 0 to obtain w equal Fa0, the integral from 0 to x of dx divided by minus Ra prime. This equation can be used to determine the catalyst weight necessary to achieve a conversion x when the total pressure remains constant. There is no pressure drop.